Hello grade 11s, welcome to our next lesson on electromagnetism. I hope you'll understand why this lesson is called the right-hand rule once we get to the end. We know that many years ago, Hans Ørsted discovered that there is a magnetic field around a conductor when a current flows. We use plotting compasses to show the field and saw that the magnetic field develops around the current carrying conductor. Today, we'll look at the shape and strength of this magnetic field. We will also see how the shape of the conductor affects the field. We will determine the direction of the magnetic field. Finally, we will find out how to draw diagrams to represent the fields. First up, in today's lesson, Kiki investigates the shape of the magnetic field around a straight current carrying conductor.
To begin our investigation, have a look at the apparatus I have here. I have a piece of copper wire that passes through a piece of stiff cardboard at right angles to the cardboard. These small plotting compasses can be placed on the cardboard around the copper conducting wire. Notice that I have placed the compasses in concentric circles. Next, I have connected the copper wire in series with a variable resistor to regulate the current passing through the conductor, an ammeter to measure the current, and a power supply. Now I'm going to turn on the power supply, and you need to look carefully at what happens to the compasses. What did you see? Let's look at that again. Notice that when the power supply is switched on, the compass needles together form concentric circles around the conductor. The compass needles remain in their new positions while charge flows through the conductor. What do you predict will happen when the current is switched off? Let's see what happens. When the current is switched off, the needles return to their original positions, pointing to the Earth's North Pole. I'm sure you'll agree that this is very clear evidence that a current passing through a conductor produces a magnetic field. The magnetic field around a current-carrying conductor is the same as the magnetic field around a magnet, but there is a difference. For a bar magnet, the magnetic field is always present, but the magnetic field around the conductor only exists when electric current is passing through it. We call this a temporary magnetic field. As with the other fields, we need to be able to represent the temporary magnetic field in a diagram. We draw the diagram to show the field lines around the conductor. In the diagram, we take a cross-sectional view of the conductor and so represent it as a small circle. Now have a careful look at the arrangement of the compass needles again and see if you can draw the field line pattern in this case. I have drawn my first field line as a circle around the conductor. This represents the first group of compasses closest to the conductor. Notice that the compass needles point in an anti-clockwise direction, so I have added in the direction of the magnetic field on my diagram. The second field line corresponds to the next group of compasses that are further away from the conductor. They also point in a circular pattern and in the same anti-clockwise direction, so I can draw in a second circular field line. This diagram represents the magnetic field at one point along the conductor, but the field has the same shape and strength all along the length of the conductor. Scientists use the symbol B to represent the magnetic field and measure its strength in units called Tesla T.
So we saw that the magnetic field around a straight conductor forms concentric circles. Kiki showed us the direction of the field. Let's see what influences the direction of the magnetic field.
In this experiment, the direction of conventional current from the positive terminal of the power supply to the negative terminal is from the bottom of the conductor to the top. Here, the magnetic field is in an anti-clockwise direction. You can see the direction of the magnetic field from these 3 compass needles. Now watch what happens when I change the direction of the current. Remember to write down your own observations and conclusions.
In this experiment, we saw the current flowing in 2 different directions. When the current flows from the bottom to the top, the red sides of the compass needles face in an anti-clockwise direction. And when the current flows in the opposite direction, that is from the top to the bottom, the red sides of the compass needles face in a clockwise direction. Let's now look at the effect of the magnitude of the current on the strength of this field.
I'm going to change the size of the current. I've placed the compasses at different distances from the conductor. Here, the current is 4,5 amperes. I'm now going to use the variable resistor to reduce the current. Watch carefully.
Did you see the difference in strength of the field? When the current strength is large, all the compass needles are affected by the field. When the current strength is small, only the compass closest to the conductor is affected. We can draw a diagram of these magnetic field lines around the current carrying conductor. Kiki already showed us that it will look like this. The circles around the conductor indicate the direction of the magnetic field. The strength of the magnetic field can also be represented in the diagram.
We can show this decrease in magnetic field strength by using a field line diagram. Remember, when the magnetic field is strong, we draw in the field lines close together. But when the magnetic field is weak, we draw in the field lines further apart.
The last thing we'll do is to learn an easy way to relate the direction of the current with the direction of the magnetic field. We relate these 2 directions using the right-hand rule for a straight current carrying conductor. Grip the wire with the right hand, with the thumb pointing along the direction of the conventional current. The curled fingers give the direction of the magnetic field around the wire. Kiki will show us how to do it.
Here you can see the thumb and 4 fingers of my right hand. Here we have a conductor. In this experiment, I know that the current is moving from the bottom to the top of the conductor. I will use my thumb to show the direction of the current in the conductor. So my thumb points up. To find the direction of the magnetic field, I use my 4 fingers. I simply curl my fingers around the conductor without touching it. Can you see here the curled fingers point in an anti-clockwise direction?
This looks fairly easy to do, but it is not so easy to draw. We can draw a 2-dimensional image of the magnetic field pattern on paper. However, the magnetic field around the current carrying conductor is 3-dimensional. The 2 sketches show the magnetic field around a straight current carrying conductor. The current in the sketch on the left flows through the conductor out of the page towards you. And the conductor on the right allows the current to flow into the page. As you can see, we make use of a dot and a cross to indicate the direction of the current. To remember the difference in direction, think of a dot. If this dot is thrown towards us, we will first see the sharp tip of the dot. This represents current out of the page. But when the dot is thrown away from us towards the dartboard, we see the cross of the flight. This represents the current into the page. So on the diagram, we can see the direction of the current by looking at the dot or the cross. We see the direction of the magnetic field by looking at the concentric circles and using the right-hand rule. And we see the strength of the field by looking at the number of field lines. Many appliances contain coils or loops in which there is an electric current. What do you think happens to the magnetic field if the conductor is bent into a circular coil? A coiled conductor is sometimes called an electromagnet because it acts like a bar magnet when the charge flows through it. Kiki will show us how to draw the diagram of these magnetic fields and explain the relationship this shows for a bar magnet. Before Kiki starts, see if you can predict the diagram for the magnetic field lines around the current carrying loop.
You could have worked this out by using the right-hand rule. Where the current is moving up, the curl of my fingers shows that the direction of the magnetic field is anti-clockwise. And here, where the current moves down into the surface, the curl of my fingers shows that the direction of the magnetic field is clockwise. These observations help us draw a diagram of the field lines around the conductor in the loop arrangement. For the diagram, imagine that the loop is cut in half and we are looking down on it. Compare your diagram to mine. Remember that the diagram represents a single conductor bent into a loop, even though there are two parts where the current moves in different directions. The current direction is indicated by a dot where the current moves up the loop and by a cross where the current moves down. The arrows on the field lines indicate the direction of the magnetic field. That wasn't too difficult, but remember that field lines cannot cross or overlap. So when a single conductor is bent into a loop, the magnetic field lines from the two parts of the conductor are squashed into the area inside the loop. Do you remember from the last lesson that a region where field lines are close together indicates the presence of a strong magnetic field? So here, inside the loop, the magnetic field is strong. You should also see that the direction of all the magnetic field lines inside the loop is the same, pointing out of the loop. Now look at the magnetic field on the outside of the loop. Here, the magnetic field direction is the same on both sides of the loop, but points in the opposite direction to the field inside the loop. Also notice that there are fewer field lines here than inside the loop. So here the magnetic field is weaker than it is inside the loop. So the effect of bending the wire into a loop clearly affects the shape of the field. Have you seen this pattern before? Of course, the shape is similar to the magnetic field of a bar magnet. Let's compare the magnetic field formed by a current-carrying conductor in a single loop to the magnetic field around a permanent magnet. Notice that in the bar magnet, the field lines inside the magnet run in the same direction close together and then loop around from the North Pole to the South Pole in two separate loops. Notice that the field lines are closest together at the poles and that they point out at the North Pole and in at the South Pole. The shape of the magnetic field of the bar magnet is very similar to the shape of the field formed by the single current carrying loop. In this loop, the magnetic field lines are also closer together inside the loop, indicating that there is a magnetic pole here. Can you figure out whether this side of the loop is a north or south pole? Well, since the field lines are pointing out of the loop here, this end of the loop must be the north pole of the electromagnet, and the other side of the loop must be the south pole of the electromagnet.
Did you see that we use the same right-hand rule as before to determine the direction of the magnetic field? The thumb showed the direction of the conventional current, and the curled finger showed the direction of the magnetic field. There is one more shape of conductor that we need to investigate before we are done. That is a solenoid. A solenoid consists of a large number of insulated turnings that form a cylindrical coil. Normally, it is made from copper wire, as you can see here, and it is turned around a cardboard cylinder. We can do the same experiment with the solenoid as we did with the coiled conductor. The results with the iron filings will look like this. The magnetic field forms circular loops close to the conductor where it goes into the page and where it comes out again. On the inside of the solenoid, there are straight lines similar to that of a bar magnet again. Now let's find out a bit more about solenoids.
Now I want to show you how to represent the magnetic field around a solenoid in relation to the current passing through it on a diagram. You will need to show the direction of the current, the direction of the magnetic field, and label the north and south pole. To begin, let's recall the diagram we drew for a single coil. In the diagram for the single loop, I had two circles representing where the current passed up and down. Now when I cut a solenoid in half and look down on it, I will see the ends of the conductor formed into two rows. On the diagram, I represent the cut ends of the conductor as circles. The circles in the row on the left all have the current flowing out and so have a dot in the center, while the circles in the row on the right all have a cross to represent the current moving in on this side of the coil. To help you complete the diagram for a solenoid with more than one loop, I want you to look carefully at what happens when you apply the right-hand rule to two conductors in the same row. Here the current is in the same direction, upwards, and you will see the magnetic field lines are in the same direction, anti-clockwise, around the conductors. Now if you look at two conductors in the other row where the current passes downwards, you will again see that the magnetic field lines are in the same direction, clockwise here. However, notice that in both rows between the conductors, the magnetic field lines oppose each other and cancel out. Can you now draw a completed diagram of a solenoid? Overall, the field line pattern is the same as for a single loop. The magnetic field lines point in the same direction inside the coil and in the opposite direction outside the coil. We can label the end of the solenoid where the field lines leave the coil as the north pole and the other end as the south pole. This completes our diagram of the magnetic field around the solenoid. Now I hope you can see that it is not difficult to determine the north pole of a solenoid by applying the right-hand rule. However, there is an alternative way which you may find useful. This is called the right-hand solenoid rule. Because there are many coils in a solenoid, the current direction is indicated by the curl of the four fingers, and the thumb points to the north pole. Let's apply the right-hand solenoid rule to this solenoid. Notice that the direction of the current is from the positive terminal and comes up on this side of the coil and down on the other in an anti-clockwise direction. If I curl my fingers over the coil, you can see that my thumb points to the left. The direction of the magnetic field inside the coil is shown as coming out of the coil by dots placed on the field lines. Now, if the direction of the current was changed to move in a clockwise direction around the coil, can you use the right-hand solenoid rule to show the direction of the magnetic field? Well, since the current is clockwise, here the direction of the magnetic field is into the coil here. We show this direction with crosses on the field lines.
The right-hand solenoid rule is a very useful rule that we can apply in lots of everyday situations. So let's recap. Today we talked about the magnetic field around a straight current carrying conductor, a coiled conductor, and a solenoid. We also learned how to draw the diagrams of the magnetic fields and the rules that we can apply to find the direction of the magnetic field around them. Next time, we will look closely at electromagnets. Until then, have a good day.